and grateful to Shmuel, who was willing to give a kind of educational talk on operator stability, and which is also kind of a preparation for next week talk. Shmuel, the stage is yours.
Okay, thank you. Okay, so almost everything I'm going to discuss is really very old. I mean, I'm starting from the example of Voiculescu, of where you have instability for Z plus Z. And then I'm going to go to some examples of Gromov and Lawson, where they showed it for, say, even dimensional hyperbolic manifolds. So those are that's the core. Part of what will be involved is the Voiculescu example can be done extremely elementarily, and it's good to have an elementary example in mind. And the Gromov-Lawson paper, firstly, it's a very, very beautiful construction. And afterwards, it was put into the context of K-theory. So I'm going to begin introducing K-theory ideas. When I say begin introducing, it's a little bit of a lie. K-theory already came up last week's seminar in proving positive results about operator stability for some very special low dimensional groups. Okay, and here we're going to see K-theory entering as a place to see that operator stability doesn't hold. Okay, so but I'm going to start off with, you know, sort of some general philosophy, because the general philosophy, I think, actually helps in connecting it to K-theory. Okay, so I want to keep in mind a question that Ulam raised. I thought it was in the Scottish book. That was what I remembered from my childhood. But when I tried to find it, I didn't find it in the Scottish book. I found it in a later publication of the Scottish book where Ulam wrote a preface. But anyway, the general philosophical question is whether every almost X is almost X, which of course sounds tautologously yes. So really what you should say is every almost X almost an X, where X is some property. Okay, so this is usual, though this is very close to the issue of testability. Let me see if, see Alex, this is an advantage of not doing it by means of scanning it in. You could actually correct them. Okay, more generally leads to lots of interesting math questions, and this seminar has been devoted to this in the context of representation theory, right? We imagine we have a discrete group and we have an almost representation. So we think of a representation as being a bunch of matrices or a bunch of permutations, okay? One for each generator. And then for each relation, we ask that the relations, not that they hold, that would be to be a representation, and almost representation means that they almost hold. And the question is every almost representation almost a representation? So, by the way, so this was where Ulam discussed this. I mean, he described, you know, I mean, it was, you know, I mean, he started off in the situation of functional equations, you know, maps from the real numbers to the real numbers, where f of x plus y is very close to f of x plus f of y. And then he began going straight to the homomorphisms. I mean, I didn't realize, but he really was starting off asking some of these questions about almost representations. Then he said, recently I became more ambitious and looked to other mathematical statements from this point of view. One could try to epsilonize, in this sense, theorems of projective geometry on conics and so on. And then he begins talking about elliptic functions. He had some very, very nice examples about, you know, derivatives of functions and things like that. I mean, he considers this as being a general way of generating mathematics. And I thought it was very clear thinking and, you know, sort of interesting. So let me give you a few examples. And
Shmuel, may I just say something about the history versus the way we talk about it today? When he defined almost homomorphism, he defined it that f of x y minus fx fy is less than epsilon for every x and y with the same epsilon, which nowadays we call it uniform stability or Ulam stability, and this was not the topic of this seminar this year, but maybe it will be the topic of the seminar we will run next year.
Yeah, you know, I mean, I think at the
There's,
level
there
of
are some
philosophy,
interesting similarities, but very
no, you're
interesting
right. No, I mean,
distinction.
right. No, I mean, as I'm going to point out, as you vary this in different domains of mathematics, you know, the answer is sometimes yes and trivial, and sometimes the answer is yes and non-trivial, and sometimes it's no and non-trivial, and sometimes, you know, I mean, it goes every which way. Okay, I mean, you know, they're different depending on what the property X that you're looking at is. You know, it's in some sense a different part of mathematics. What I want to do is I want to just give a couple of examples, which in the end actually, although they look disparate, they actually are in this beautiful history connected to one another. Okay. So the first example is actually, you know, just in basic analysis. You know, you have some functional A and you have a, you know, so a functional, my impression is that's a function on functions. Okay, so that you needed to have a, you know, before mathematics was abstract and that functions became points in function spaces, right? I mean, they wanted to have a different word, I think. So anyway, so you have some A of Fi and they're going to 0. And you'd like to know, does that mean that there's an F where A of F equals 0? Okay, and this was involved in trying to solve the Laplacian. That was the Dirichlet principle. And of course, we know what happens. You know, as you begin doing this, there are many different notions of convergence, which, by the way, in this seminar has the analog of having many different norms that we choose on unitary representations. Okay, and sometimes you expand the notion of what you mean by a solution in analysis, right? I mean, we have generalized functions, distributions, and this is very related to the idea of invertibility. When you have, say, a map between Hilbert spaces, A, say a linear map, right? And if you have a B such that BA is identity plus compact and AB is identity plus compact, right? Okay, right? So that's something which you would say is almost invertible. Okay, and the natural question that you could ask, right? The first of these sort of questions, but it's okay. So here the idea is to think of compact operators as being small. Okay, I mean, I'm not putting in a specific epsilon here. And the question then is every such thing of the form something genuinely invertible plus compact? Okay, and the classical answer to that is that no, there's an obstruction. Okay, and that obstruction is called the index. The index is, it turns out that this condition is enough to tell you that the dimension of the kernel is finite and the dimension of the co-kernel is finite. Okay, and it's not trivial, but it's a fact that if you were invertible plus compact, those two dimensions would be the same. It's like, right, the rank and the column nullities of a matrix are the same, right? So that extends to, in infinite dimensions only to invertible plus compact, and that gives you an obstruction, okay? At the moment, it's just a sort of an example of Ulam's philosophy, but it actually is very much behind the scenes of the mathematics that's going to be entering into Marius's talk next week, I believe. I mean, okay. Another example of this kind of philosophy is the question for a group gamma of property T, right? For property T, right, you imagine that you have, right, that you have a unitary representation of the group gamma, and then you're asking, if I have an almost invariant vector, is it true, right, where you have epsilon almost invariant? You ask, is it always true that this almost invariant vector has to be near an invariant vector? Okay, usually we say, does there exist? But asking whether it's near is the same thing, right? Because you could look at the orthogonal complement of the fixed set. Okay, so property T is something that we've grown to know and love. And that's an example of the Ulam question, you know, with respect to fixed point sets. Expander graphs are the same kind of thing, but there you're asking, you're looking at subsets and you're asking, if you have a subset whose boundary is nearly empty, does it mean that it's close to something whose boundary is empty, which means that it's either close to the whole thing or that it's close to nothing. Okay, so, okay. I want to now mention, this is one of my favorite theorems, and I find it irresistible. Whenever I have an excuse to talk about it, I do talk about it. Okay, so here's a problem in topology, which well, here's a theorem. Okay, let's go. Okay, so it says this: for every closed manifold, I need a metric in order to measure distances. Then there's some positive, so closed means compact, no boundary, okay? Then there's some epsilon, so that if you have a map from M to any other manifold of at most the same dimension, let's say everything is connected, okay? So what we'd like to know is whether F is a homeomorphism, okay? Well, right, so let me just write that, right? So F is a homeomorphism. That just means, okay, I'm assuming that N is, everything connected, Mn connected. That just means that the diameter of F inverse N is equal to 0, right, for all N in N, right? That the inverse image of each point is a point. Okay, a little technical point, you need a little exercise that if I have a closed manifold and I embed it in another closed manifold, it has to be onto, okay? Okay, that's a little exercise in, say, degree theory or something like that. So to be a homeomorphism means that the diameter of the inverse image of every point is 0. So now you could say, if I have something that's an almost homeomorphism, what would I mean by that? Oh, I'll mean that the diameter of the inverse image of every point is less than epsilon. Okay, and the question is it the case that every homeomorphism can be, every almost homeomorphism, is it really true that every almost homeomorphism can be moved to be a homeomorphism? Okay, so like with a statement of this sort, it might feel that it's either trivial or it's false or whatever. I'm not going to take any votes here because I already prejudged it. I called it a theorem. So this theorem tells you, that if you can get a map to have diameters of point inverses very small, then you've almost made it into a homeomorphism. Okay, if at some point you get sick of the talk, you might enjoy as an exercise to deduce the Poincare conjecture from this. Okay, so this is an example where it's not trivial. Okay, it's in fact this is sort of a deep general case where you have some kind of stability in this sense, and there is an analog where instead of trying to control points, if you have a map from a manifold into a product manifold and you do something suitable, then algebraic K-theory enters. So there's some foreshadowing of themes. Okay, let me now get to the topic. Okay, but so you have a group generated by gamma 1 through gamma k. Let GI be a sequence of compact groups with bi-invariant norms. Okay, and we want to know whether okay, you can see what kind of analyst I am. If for all delta there exists an epsilon such that every epsilon almost representation, okay, so that means that the relations hold, okay, to within epsilon is within delta of a representation. Okay, so this is what we mean. And for each, you of course have to specify what you mean by the metric on these groups. Okay, there are modifications allowing post-compositions, right? That's what people sometimes call what? Stable stability? Is that what it's called, Alex? Flexible stability?
Yeah.
Okay, right? You have an almost representation into UN, and then you're willing to go into UN plus 5 or into a bigger group when you do the approximation. Okay, that's a variation on the theme. Okay, and for this talk, what we're going to be always doing is we're going to be using the operator norm, okay? And that for defining the distance. Now, if we fix a particular I, okay, then it's clear that the answer is yes, okay? You're dealing with a product of unitary groups, right? Some finite product of, a product of unitary groups, so that is compact. Okay, and then of course you're looking at some function, and there's no issue, right? I mean, if you take any sequence, any kind of minimizing, you imagine that you have delta I, which can't be approximated, then you take the limit of them. Okay, and then you end up on the on the solution set. Okay, so there's nothing to discuss for a given I. This is an asymptotic problem. Okay, so so let's talk about some simple cases first. So if you look at Z mod K, it's generated by one element. Okay, so an almost representation of gamma is just an A in the unitary group, and D mod will be getting larger, such that A to the K minus the identity has small norm. Okay, but in that case, what are we trying to ask? We're asking, if I have such a thing, how far is A from a general root, a genuine root of unity, right? A general matrix of roots of unity. So of course, what we just do is we diagonalize. Okay? And when you diagonalize, right, you have these various eigenvalues, and we're asking, right now notice that we're using the uniform norm. So we're just asking that each individual lambda I to the K is within epsilon of the identity, of epsilon of the number one. Okay, so what you do is you then look at the closest root of unity, and then if you think about it, taking kth powers stretches. So in fact, if you're within, knowing this within epsilon, that tells you that the lambda i's are actually getting quite close to the roots of unity. Okay, so that immediately gives you a by hand argument. You'll notice the dimension doesn't enter in any way. So this we just proved stability for the finite cyclic group. Okay, it's a completely elementary fact. Okay, in general, finite groups are stable. For people who have been in the seminar, it's not so hard. I mean, there are cohomological criteria for stability, and then cohomology of finite groups tends to be pretty easy. Free groups are stable because free groups, there are no relations to hold. I guess, right? So the next case to consider is the group Z squared, okay? And this is the one that was discussed by Voiculescu, okay? And here is the basic idea, okay? Let's think about this function where I take T, okay? I mean, it's unfortunate. I mean, I think that my notation is not consistent from one slide to the next, but I hope that you'll survive with it. Suppose that we think about this where T goes from 0 to 1, okay? So if I look at 1 minus T times UV plus T times VU, and I take, okay? So firstly, before I take determinants, that's a path from UV to VU. So if they, right, it's the straight line path, okay, through the matrices, okay? It doesn't stay unitary, okay? But I take this straight line path, fine. And if U and V commute though, then UV and VU are the same as each other, and this path is a constant path. Okay, now even if U and V don't commute, the determinant of U times V and the determinant of V times U are the same. Okay, so no matter what, this is a closed loop. Okay, and it's constant, right, for commuting matrices. Okay, so now the method, and this is due to Excel and Loring, and I don't know, this is, you could see I didn't even bother copying it into my own handwriting, and I just copied it straight from the journal. Okay, from the proceedings of the AMS. The idea is to just consider the winding number of these curves, right? Given matrices, U and V, right? You will always get this closed curve, okay? You have to be careful that the closed curve doesn't go through the origin, okay? But the point will be that if U and V almost commute, then that will, right? So then UV and VU are very close to each other. This loop, right, doesn't have a chance to get near zero, okay? So, okay, so this is, right, we have this closed loop. To talk about the winding number, right, the winding number around zero, right? So to have a winding number around zero, you have to make sure that this loop, right? So notice, this is a loop in the complex plane, right? The determinant is a complex number. Okay, this is very elementary and beautiful, and I'm afraid I will lose people because I know I'm not a great expositor, but I shouldn't lose anyone yet. So, okay. So, right. So if U and V almost commute, right? So then, so then UV is here and VU is there, right? And, we're just looking at some path that's very, very close, right? Here, the determinant is what, let's imagine U and V are unitary, right? So here the determinant is 1 and there the determinant is, right? Well, whatever. I don't really care. These are both determinant alpha, and along here, you're very, very close to alpha, right? Where the norm of alpha is 1, you're very, very far away from the origin. No, well, that would be, if you and, I take that back. That was a lie, and that's exactly what we're trying to avoid. Okay, never mind. What I wanted to, okay, let me start again, right? Whenever we have whenever we have any pair of matrices, we have this closed curve in the complex plane. Okay, if they're almost commuting, right, then that closed loop stays away from the origin. If they genuinely commute, that loop is a constant loop. Okay, okay, and now here is the main result. This is Voiculescu's example. Here are 2 specific matrices. One of them is the shift. So you're on an n-dimensional complex vector space, and you're just shifting by 1, and then the last nth vector wraps around and becomes the first vector again. Okay, that's what S sub n is, right? So it's a nice unitary. Omega n is in fact a diagonal matrix. Okay, and along the diagonal, you're having the nth roots of unity put in order. Okay, so omega n, is it's like 2 pi over n away from 1. Okay, it's very, very close to the number 1. Omega n squared, right? And you're going around these. These guys are very, very close to each other. Okay, so when you look at when you conjugate omega n by Sn, right? What does that do? That just permutes these diagonal entries. Okay, so it's so these are the basic facts, right? So I mean, the difference between them is 1 minus omega n, right? So they are almost commuting as n goes to infinity, right? They're going, okay, and then there are some facts that you just use for the course of verifying things. So let me now just, I'm not going to go through absolutely every detail, but the point is you're looking at this curve. Okay, now here R is the variable, is the time variable. Okay, and what you do is, okay, you imagine that you have X and Y are going to be the things that are close to omega n and Sn respectively. Okay, and right, so what should I call this? I mean, right, I mean, we could call this integer, the W of UV, right? And it's an integer. Okay, that's sort of the key feature that's set up. And the basic point is, right, that now they just take the homotopy that compares A sub t is what homotops A to omega n. Okay, right? That, after all, they're supposed to be close to each other. And similarly, B sub t, is what moves B to Sn. But again, to say that these are close in the operator norm, right, is extremely powerful. And then the point is that now for every t, you have a curve, right, corresponding to these, A sub t's and B sub t's. At one time, you're having the genuinely commuting thing, so you have winding number 0. At the other time, the other point, what happens is you get a little calculation, and and it turns out that if you look at this determinant, which they compute explicitly, it turns out that you get it's the line segment that moves from 1 to omega n to the nth power. So you start off with that linear line segment, and then you're taking the nth power of it. So as you move around the segment, you're going from 1 all the way around the circle. right? So it winds around the circle, right? Since it's omega n bar, it's actually the other direction. Okay, it doesn't matter. So you've gone around it once clockwise. So in that case, the winding number is -1 by our usual conventions. Okay, and that's the complete proof. I mean, all of these, estimates are just, what you need to check that at all of the times in between, you never are going through 0. Okay, but the idea of the argument, I think, I hope is clear. And
Shmuel,
yes.
Shmuel, can you explain? Okay, so you explained why the winding number is 1 or -1 in this case, and not 0. Why is the conclusion that there are no close by matrices that actually commute? I don't see it right away. Maybe.
Oh, okay. So here's the idea. Okay. So, okay. Suppose this is near, I'm going to use their note. Suppose this is near X and this is near Y. Okay. Now, the thing that they do is they take AT is the straight path from X to Sn. And here they have put in the BT being the straight path from Y to omega n. Okay, so at time 0, you're at xy. At xy, this curve is the trivial curve. It has winding number 0. Okay, at every time in between, you get some curve. You get some closed curve in the complex plane. Okay, you have to do some little estimates. Okay, and that's where these little, there are some little inequalities here. Okay, that's the estimate that at no time in between do any of these curves pass through 0. Okay, so if they never pass through 0, they have the same winding number. One of them is the constant curve that has winding number 0. The other curve is the one that has winding number -1. So therefore, you couldn't go ahead and have the approximation. Okay.
Yeah, but you do have an approximation that depends on n, right? Like if you allow, as you said before, like if you allow n to get into the approximation, you should be able to do that. So
no. Notice the dimension is going up.
Yeah, for a fixed. Yeah, clearly for a fixed n. No, I'm not.
No. Yeah. So for the. Yeah. No. So I mean, I'm not understanding what. So what do you mean that there's an approximation for a fixed n? The approximation is some big number.
So they are. So there are matrices that commute and are I don't know, 1 away in operator norm from these matrices, right? Like very far, but still some.
Yeah.
Like,
right. So over here,
where does this kind of argument falls when they are?
It's in checking that you never go through the origin. Okay? What you need to know is that for every t, okay, so right, this is checking that for every t you don't end up going through the origin. Okay, that's what this sequence of inequalities is doing.
And this needs the almost commutativity of the original matrices?
Yes, yeah. Yes.
Thanks.
Okay. Yeah. No, so I hand waved on the inequalities, but that's actually a matter of taste. I mean, I don't think that I ever publicly like doing inequalities. I don't even privately enjoy it so much. Okay. Okay. So next week, so this is my advertisement. Okay, but Marius will show that, for example, I mean, he's going to prove more than this. He's going to show whenever you have a linear group and some even dimensional cohomology with rational coefficients is non-zero, then the group is not operator stable. Okay, so so the Voiculescu example that we just did is a special case of this. It's the case of z plus z, which is certainly a linear group. Its second cohomology is non-zero. Okay, so this is sort of a much stronger generalization. And what I want to now do is explain to you the main mathematical goal is probably to tell you about what Gromov and Lawson did for uniform lattices in O2N1. Okay, there are going to be some subsidiary goals. I mean, I'll talk about what happens for orthogonal matrices a little bit instead of unitary matrices. At least I hope to. it turns out that elements of finite order have a special role in the theory, and that has some implications for some groups that you think of that are very beloved in this seminar, where you apply the Garland method and you know that all the cohomology is rationally concentrated in odd dimensions. Nevertheless, you can sometimes use the same methods to go ahead and see operator instability. And you might ask some kind of quantitative questions. Okay, so the relevant kind of geometry. So the construction by Gromov and Lawson is a geometric construction. And what you need to know about is bundle theory. And then K theory is just sort of organized bundle theory. Okay, so by the way, I'm not going to get to talk about K theory of operator algebras. I was thinking about would I be able to get there, and I won't. I'm going to just be talking about the K theory of spaces. Okay, but still, okay, so let me just remind people about things related to bundle theory. And this was part of what Alex told me I should emphasize, because some of the participants, this isn't the natural language for them. Okay, so a bundle, let me remind you, is you start off have a base to the bundle. So you have this space X, okay? And you have a space E that maps down to X. Pi is called the projection. And to be a bundle means that over each point of X, you have a fiber, which is what I drew those vertical lines. Okay, but you should think about them as being vertical vector spaces of some dimension. Okay, then to be a bundle means that not only is each individual point a vector space, you have some kind of coherence among these, which means that when you can cover X by little open sets, like the definition of manifold, right? Where locally you're not supposed to have much geometry. So too for bundles, you're supposed to locally not have any kind of interesting phenomenon occurring in this family. Okay, so that means that the inverse image of each of these OIs should be OI cross V in a way that's compatible with the projection. Okay, we'll talk about, and then over the intersection, then you want to say that, the way I view it over the different open sets, they should be linear, they should be fiber-wise linear isometries. Okay, strictly speaking, I just defined the notion of a bundle together with a metric, but every vector bundle has a metric on it, and we're not going to be studying the metrics on bundles, so I'm going to just live with that little. So let me just give some examples, okay? Because for me, examples are better than actual definitions. So the first example is the Mobius strip. So I think everyone knows the Mobius strip, right? I mean, this is my artist conception of a Mobius strip. So it has this center circle. The inverse image of every point is an interval in the usual finite Mobius strip, but you could have imagined it being a real line, okay? Now, what's funny about the Mobius strip is that when you go around, you glue it back to each other with a flip. That flip on the real line is just R goes to minus R, okay? That's a linear isomorphism. Okay? So this is a good example of a vector bundle over the circle. I could go ahead and try to do the same thing. The torus, I'm imagining the torus as being the unit circle in the complex plane. If I want to twist by an angle theta, right, then that is multiplying by e to the I theta. Okay, so I could think about this as being the center of complex lines. Okay, and then I would get a bundle, a complex line bundle over the circle. Okay, and it's sort of interesting, right? I mean, I could think of it, right? I think about it very, very concretely, right, as being, I just take these vector spaces and I glue them along, and then my gluing data when I come back is I glue back with a twist by e to the I theta. To a topologist, that vector bundle turns out to be a product bundle. It's not very hard, and the hint is just take a path from the identity to e to the I theta and incorporate that twist as you go around. Okay, so so here, what I did was let me just talk about what I did. I had a representation of the group Z, and I associated to that representation of the group Z, I used that as my information to construct a certain bundle, a certain C bundle, right? It was a one-dimensional representation. That was why I used a C. And I built a bundle over the circle. It happens to be that that representation is connected to the identity through representations. So I had a very easy argument that is topologically trivial. There is an isomorphism of bundles, okay, that connects them. So there, okay, but in terms of an example of a vector bundle, it's a boring example, but in terms of this seminar, it's maybe an interesting example, okay? Here's another bundle. If I think about the two-sphere as being the Riemann sphere, okay, and right, so it's a complex manifold, and then I think about its tangent space, just like the tangent, so I'm assuming that you know the tangent space of an ordinary manifold is a real vector bundle, and the tangent bundle of a complex manifold could be viewed as a unitary bundle, okay? So this is this is an interesting example of a bundle, okay? And it's morally related to the Voiculescu example, when we begin putting things into some kind of bundle theoretic context. Okay, but anyway, this is a good one to think about, because if you're like Alex, I don't mean to say anything negative about Alex, but Alex always likes to see the group in everything, okay, you know, which is, I guess, like always wanting to see the positive in every circumstance. But here, the two-sphere has no fundamental group, so it's a little bit hard to see what is non-trivial about this bundle. I mean, when you first see bundles, you say, well, think of the tangent space really is the same everywhere. Where is it different? How is it non-trivial? But you know it's non-trivial because you know the Harry-Ball theorem, right? You know that you can't find a non-trivial section, right? That there's nowhere vanishing vector field, right? It's a subtle phenomenon that this bundle is a non-trivial bundle, okay? But it is, and we'll get later, I'll return to how we know it's non-trivial, and you'll see that a winding number enters, and that gives you the path, so to speak, the connection between the early Voiculescu things and, you know, some of these other things that we're going to be discussing, okay? But, okay, so now if M is compact and I have a representation, either an orthogonal representation or a unitary representation of the fundamental group, then I could always build a bundle, right? So this is like what I did in the case of the circle. So let me just point out what I do. I go to the universal cover of M, right? This has an action of the group gamma. So does whatever the field is, whether it's the real numbers or the complex numbers, that also has an action of gamma, right? So gamma acts on this by covering translates. Gamma acts on this. I could look at the product action, right, on this. And then I look at the quotient by gamma. And when I project down to M tilde mod gamma, just forget the F coordinate. Okay, then I get a bundle over M, right? So this thing here is the original space M. When M was the circle, that's a way of describing the construction that I did before. Okay, before I would think about M as being a fundamental domain and I make identifications, and there I was using the representation to make the identifications. Here I'm just phrasing it all at once without picking a fundamental domain. Okay, so this is a little bit more elegant, but the other is a way that you might really want to think about it concretely. Okay, so now the idea is this gives you a method of trying to study representations via topology, right? You're given a representation, you now associate a bundle. We've discussed the Harry-Ball theorem, right? That there are methods that topologists have for studying representations, for studying bundles. So now you could try to study representations via bundle theory, okay? So here's sort of an example. If you go from ZK to the unitary group, you could then let your manifold be some sphere of high dimensions, like the unit sphere in complex N space. N has nothing to do with D, okay? But it turns out that as N gets bigger, you have more and more information when you look at this space, okay? So now you have the sphere, and then you could go ahead and produce this product, and that defines for you a d-dimensional complex bundle over this space. This space here is classically called a length space, okay? And using this, you could try to study the representations of Z mod K, okay? I mean, not that it's such a great thing to study the representations of Z mod K, but, okay. So let me just, okay. So there are some key constructions on vector bundles, okay? And so let me just, okay, so here, okay, so suppose that here's X, here's Y, and I have a vector bundle over X. I have E over X. So the pullback, F star of E, just as I look at this point, I look at its image. If over there I had this vector space, I just go ahead and I put the same vector space there. Okay, so when I'm going to talk about vector bundles, I'm going to be very imprecise. What I'll just imagine is I associate a vector space to every point. I won't talk about their continuity and compatibility, although you need to do it in order for it to be rigorous, right? But in order to think about it, just think about it as an assignment of a vector space at each point, which you do in a careful way, just like a function is an association of a function of a value at every point, and that, you know, of course, if you want to be continuous, you have to be careful to not let the value change too much as you move around. Okay, so if I have this map from y to x, at each point of y, I know which vector space to choose. And if this point there goes there, then I put that vector space. Okay, so that's called the pullback. Okay, and pullback constructions are again important in topology. You pull back differential forms, you pull back cocycles. Okay, so there's a contravariant structure to the theory of vector bundles. So when we go ahead and invent, so to speak, the K-theory of X, which is going to mean the vector bundles on X, this is going to be like cohomology. Okay, and it's going to involve, it'll be a contravariant generalized cohomology theory. I mean, those are some of the fancy words. Okay, and then Whitney sum is again the idea. If I have two vector bundles over the same space, I could then at each point, I just take the fiber in each of those bundles over it, and I just take their sum. Okay, any kind of linear construction you could do to vector spaces, you can do to vector bundles. Okay, so for us, I'm just going to focus right now on pullbacks, and there are sort of two things that are relevant to us that come out of the theory of pullbacks. One is that there's actually a best M to use when we do that construction associated to a representation. Okay, remember, in the case of pi 1 equals z, right, I said use the circle, right? And I showed you this bundle over the circle. Then I said you could take any space whose fundamental group is z and do the same construction. But actually the circle is the most efficient one. Okay, no other one has more information than that. Okay, and what is the reason? The reason is that any m, if pi 1 of m equals z, it's a theorem in topology that there's a map from m to the circle that induces an isomorphism on pi 1. Okay, and then it turns out that the construction for rho over here pulls back to the construction over here. So there's no information that you get by looking at more general manifolds than the circle. You might as well just look at the circle. That's where all the information is. Okay, and that what you're most interested in is a space that's like the circle. You want a space B gamma so that for any m with pi 1 of m equal to gamma, you get a well-defined map from m to b gamma. You'd like there to be a unique up to homotopy map that's an isomorphism on pi 1. Okay, so this is old-fashioned topology, from the first half of the last century. Okay, that for every countable group, say, there is such a space. It's not necessarily compact. That's an interesting question. Given a group gamma, when can you make this kind of thing have finiteness properties and so on? But it's sort of a basic construction, okay? So let me just say, so this B gamma, it's a space associated to gamma. It's not quite a unique space, it's a unique homotopy type. And B gamma is to gamma the way a circle is to Z, okay? It satisfies that universal property that I told you. So the torus is what's associated to Z to the N. The surface of genus G is what's associated to this group. And, lots of things in geometric group theory have to do with trying to turn groups into understanding things about B gamma without actually having a direct construction of B gamma. Okay, so that's sort of one place where it's relevant. Okay, that the next thing that we could do is that arbitrary bundles over arbitrary spaces can be classified thanks to this pullback construction, okay? So I have to say a word or two about that. So if I have d-dimensional bundles, they're in a, over X, they're in a one-to-one correspondence between that and maps from X into a Grassmannian. So let me just tell you what the Grassmannian is. The Grassmannian is, this is the space of FDs in Fn. Okay, so for example, if D equals 1, right? So we're going to be talking about line bundles, either real or complex line bundles over X, right? So what is this Grassmannian? They're one-dimensional vector spaces inside of, either Rn or Cn. So what is that? Oh, well, we know what that is. That's either Rpn minus 1 or Cpn minus 1. These are projective spaces, okay? And what I'm saying is that every line bundle on X is pulled back from a line bundle over the Grassmannian. Now, by the way, the Grassmannian has a very trivial bundle over it. It's a non-trivial bundle. I mean, it's a tautological bundle. A point on the Grassmannian is a vector subspace of Fn. Oh, so then we have a vector bundle over there, right? I mean, I told you what vector space you associate to each point, okay? And everything comes back from the Grassmannian, okay? This will be important. Yeah.
Shmuel?
Yes.
So here you mean it corresponds to continuous maps from X to the Grassmannian?
Yes, yes.
Ah, okay. Thank you.
Yeah. So these are up to isomorphism, and these are up to homotopy. Okay. I don't want to discuss any. Okay. Yeah. So here's a rough idea. If I have X and I have this vector bundle over it, I imagine sticking my X, the whole total space, into some big Fn. And then at each point, I look at that vector space as being a subspace just of that Fn, maybe move it to the origin. So then at this point, so that defines for me a function, right? What's on here is the Grassmannian, right? I mean, I apologize for my handwriting. Right on this side, I have the Grassmannian. Okay, and I have this tautological construction, right? I mean, at each point of X, if you made it, let's say you did it smoothly in some sense or something like that, then, right, then here I would have, if you like, the differential of however I embedded it. Okay, I'd really get a linear space, and that linear space would be varying from point to point, and that gets me a map to the Grassmannian. So now what can we do? Okay, so what's the idea? Okay, so here's some description of what the Grassmannian is, and here's sort of the ultimate, here's the point. Okay, I'm sorry. Turns out that, so this is, let me tell you, so this is the Grassmannian. And the cohomology of the Grassmannian turns out to be a polynomial algebra. There's a class C1 in dimension 2. There's a class C2 in dimension 4. There's a class Cn in dimension 2n. And it turns out that linear combinations of powers and products of these, that's what all the cohomology is. But now what can I do? If I have a vector bundle over X, right? What I could just do is I then get the map from X to the Grassmannian. Okay, let me call that thing phi sub E, being the associated map. And then C sub I of this vector bundle is just by definition phi sub E. You pull back those particular cohomology classes on that particular space. Okay, so again, for projective spaces, those are so explicit, I think everyone in their first year class, topology class, knows how to compute their cohomology. This is a much less obvious thing that for the Grassmannians, they do have cell structures. There are various ways there are lots of proofs of why the cohomology looks like this. But this says that there are cohomological invariants of vector bundles. Okay, and that we have cohomology and what's philosophically important is that we have cohomological invariants in every even dimension, not just dimension 2. Okay. Okay, that's the takeaway. Okay, there are more direct definitions, and unfortunately, I can't. I'm looking at time, and I'm getting a little despairing. okay? It turns out that when you do that example for Z mod K, Ci is the ith symmetric function of the rotation numbers. Okay, it turns out the 2ith cohomology of that length space is Z mod K, right? If I wanted to describe, for each, right, if I look at a representation of Z mod K, right, I mean, I have some rotation numbers, right, which are, which is, you're always each eigenspace is multiplying by some multiple of 2 pi over K. Right, so you're having these things in ZK, and then the CIs are just the symmetric functions. Okay, so it turns out that for primes, these cohomological invariants detect the representation, but if you're composite, they usually don't. Okay, I mean, just to get some feel about what this looks like, that part isn't immediately relevant. So what does C1 measure? This first one. Okay, so let's first do it for a line bundle. Okay, so what you do is you take a section of the line bundle, okay, which doesn't, some generic section, so it doesn't vanish more often than it has to, which means that, okay, so at vertices, you have no trouble making the section non-zero. On the edges, well, I mean, over an edge, your thing looks like C cross an interval, okay, right? So, and it's non-zero at this point, it's non-zero at that point. So I just connect it because C minus 0 is connected. I have no trouble. But now for each 2 simplex, you've done it on the boundary. You've taken a section, you've done it on the boundary. It's been non-zero on the boundary. So for each 2 simplex, delta, we're going to define C1 evaluated on that delta. I'm defining a cochain. It's the winding number of that section around 0 in the using the trivialization over a 2 simplex. Okay, now you might change what you do on delta 1, on this one simplex, on this original triangle, you might think, okay, I got some cochain, it turns out to be a cocycle, and and it looks to me that some winding number is non-zero. If the winding number is non-zero, it means that I can't extend those sections and make it trivial. But of course, what you might want to do is then change it on one of the faces, right? I mean, on one of these edges. But of course, when you change it on one edge, then, when you change it on delta 1, it's going to influence delta 2. Or if you change it here, it's going to influence delta 3. So what ends up happening is you get a well-defined cohomology class. That is C1. And you see it's built up out of winding numbers. So that was what I was saying, that this Voiculescu example is associated to C1 of a bundle. In general, I just explained to you what you do for a line bundle. If you have an n-dimensional bundle, you do something similar. You first choose, you have no trouble choosing n-1 sections and getting getting all of them to have 0 winding number. It's just the very last one that you run into trouble with. And it turns out you can take the winding number of that, and that defines for you the C1. So it's really the Voiculescu winding number thing. And I think I'm going to not do this example. It's working out the case of vector bundles over the 2-sphere. And then what you do is you go for, there's some gluing map along the circle, right? I mean, on the left side and on the right side, these bundles are trivial. What's non-trivial is how you glue them together along the center circle. And you can now just take the determinant of the gluing map. It's a map into some unitary group. And that determinant, therefore, has a winding number. The determinant of a unitary matrix, it lies in the unit circle. Okay, and that's what this C1 story is. Okay, so doing all of this with respect to the higher CIs is a generalization of the Voiculescu idea. And that's what we're going to be using in the Gromov-Lawson story. Okay? But what I have to do, I haven't explained one very important thing, which is in the Voiculescu example, I had to explain, why is it that if they almost commute, the winding number is 0, right? So I still haven't explained enough about Chern classes to tell you why, if this thing is almost a representation, why do the Chern classes vanish? Okay, that should be the punchline, except that I also already gave you an example which shows that the Chern classes don't vanish, right? For the group Z mod K, the Chern classes don't actually vanish, right? We saw that they lived in Z mod K and that they were symmetric functions, right? Blah, 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 blah. That's not called vanishing, okay? So in order to do that, that's where you have to go to the work of Chern, okay? So the first thing is there is a bundle associated to an almost representation, okay? And so for a representation, right, so this was basically what you, right, the thing that I explained before, what you do to a representation, okay? And what you want to do is you would like to do something similar for almost representations, and you still want to go ahead and you build a bundle over B gamma. You still build a bundle over B gamma, okay? But this bundle will not be as good as the bundles that come up from genuine representations. So in order to understand what the difference is, this involves the idea of connections and curvature, okay? And I'm gonna have to be somewhat imprecise, okay? So a connection is, right, so we talked about bundles, okay? And a connection is an additional piece of structure on a bundle. It is some method that tells you how you go from a fiber to a nearby fiber, okay? I'm not going to tell you how you encode it in a differential operator or anything like that, right? That's like, you know, just like tangent vectors are, they're derivations on the, you know, on germs of functions, etc. Right? I don't want to use that language. We know what a tangent vector is. It's an arrow at each point. So too, a connection is a way of going from a fiber over one point to a fiber over nearby points, infinitesimally nearby points. Okay, so what I want to do is, let's think about one of these vector bundles over the two sphere. And instead of going all the way, you know, by, I still wanted to go around once, right? That as I go around this, right, I'm going to be multiplying by e to the I theta. But instead of doing it all at once, on the purple, let's imagine you don't do anything. You just glue by the identity map. And on the red, you go twice as fast, right? There you do e to the I 2 theta. Okay, so topologically that doesn't change anything to the bundle, but now I have this sort of this funny way that I did the gluing. So now, what happens when I want to go from the east pole to the west pole? Okay, it's pretty funny. I mean, having drawn it this way, I don't have north and south poles. But anyway, so if I move through the purple, no matter when I perturb a little bit, right? So I go from fiber to fiber and I use identifications. You know what I mean when I say following the path, right? Because the path is always locally inside one of these charts, right? There's some interface, but no matter how I do it, if I go, you know, the top wiggly way or the bottom wiggly way, as long as I'm just going through the purple, I end up with the same vector all the way to the right when I go from left to right. Okay, on the other hand, if I go through the red, depending on where I go through the red, that's going to twist the identification a little bit. Okay, I mean, if I twist in one place and a nearby place, it's only going to change the identification a drop. It's a continuous amount, okay? But it is not the case that small perturbations, you know, don't affect it. So now what happens? When we do this example for representations, you always have what it's called flatness, that nearby ways of translating give you the exact same way of getting around. Okay, so think about that example over the circle, where we went to rotation by theta as we went all the way around the circle. Okay, no matter how I go, you know, no matter what I, you know, in terms of a connection on the bundle, right, that connection is different than the trivial connection. All of those bundles were the trivial topological bundle, but as bundles with connection, right, firstly, it's a flat bundle, no matter how I go. For the circle, there's only one way to go around the circle, right? Or if I go around it twice, right, anything that, you know, for each homotopy class, right, the thing that goes around k times, it will multiply the vector in C by e to the, you know, e to the I alpha times k, right, e to the I alpha k. Okay, I mean, that's sort of the whole story. And here you could see, right, and this is, okay, so I hope that this idea is clear, right? You use this local coordinate charts and you do the gluing. You might use some other methods for defining connections, but the key thing is, and the real question is, if you have small loops, right? Right, understanding the difference between nearby loops is the same thing as understanding what happens. Nearby curves is the same thing as understanding small loops. And the real question is, if you have a small loop in your space, and you go around a small loop, is it the case that you will end up someplace different than where you started? Okay, and in this example, if your small loop is over here, the answer is okay. But if your small loop is over here, no, you had one rotation when you crossed, right? When you cross going from left to right, and then you rotate back by a different number when you go from right to left. Okay, that phenomenon is called curvature. Okay, and when you make it all rigorous, curvature comes out to be a 2 form, and the nth Chern class is a trace of some exterior power of that form. Okay, the formula is not important. Okay, the thing that's of key importance is, okay, so firstly, it turns out that these are integral cohomology, and that's based on a calculation on the Grassmannian, another advantage of the fact that there's just one space that you have to look at, and that Grassmannians are compact. Okay, but if the curvature were 0, before we talk about what happens if the curvature is small, if the curvature were 0, well, then I'm taking, right, this differential form, this is an expression in de Rham cohomology. If this differential form is 0 everywhere, right, that it's a flat bundle, then this is 0. So the de Rham representative is going to be 0 when you're flat, which means if you come from a representation, you get 0. That's the analog of the statement that if the things commuted, then the winding number would be 0. Okay? And it's for the same philosophical reason. Here it's that some differential form is identically 0. There it was because some curve was the constant curve. Okay? That part isn't, it's not something to write home about. Okay? But now the next point is, if I'm on a compact space, and if the curvature is really, really small, okay, so now this differential form, right? I told you that these Chern classes, they were really living in integral cohomology. Okay, so if they're very small as a de Rham class, they're going to have to be very close to 0. But on the other hand, the integral stuff is a lattice. If I have something in a lattice and it's very small, then it has to be 0. Okay, that's the miracle. It's not just the fact that topologists have Chern classes that they could define. What's also important is the Chern description of what Chern classes are, that they can be described in terms of curvature, and that the curvature is reflecting what goes on. So now here's the more sophisticated view of the Voiculescu example. If you do it on a torus, and here you do the gluing, you have to cut out some kind of particular error things because they don't genuinely commute. What you would then have along these this missing little square in building the bundle is something that's associated to this commutator. That commutator is close to the identity, so you choose a path to the identity. Now that path is like the red side of, it's so to speak, like the red side of that 2 sphere that I was talking about. So that introduces some curvature. Okay, when you go ahead and have that piece, and then that defines for you a bundle over the torus. Okay, and as n gets larger, that thing is getting closer and closer to the identity, so therefore that bundle is having less and less curvature. Okay, and now you could rephrase okay, by the way, I apologize. What I've done is I've taken what Voiculescu did, then Exel and Loring gave a very beautiful elementary distillation, and I blew it up again. I apologize, but it's sort of necessary for the other aspects. So flat bundles over X, those are the ones where locally you don't, small loops don't twist. Those correspond to bundles with 0 curvature. This generalizes to a correspondence that almost flat bundles over X, if X is a finite complex, correspond to bundles with small curvature. Okay, and that's, there are different versions in different papers of this. And the key lemma is that an almost flat bundle over a simply connected space is always topologically trivial. But what almost means is, we imagine this is a finite complex, it has a metric, and then this epsilon, of course, depends on the metric on X. Okay, I mean, for this quantitative thing, because after all, if I take X and I rescale it, I just multiply everything by k, the curvature turns out to get multiplied by k to the minus 2. Why? Because the small loop here is much larger over there, right? I mean, what's going on? We're having different identifications when I go around this loop, right? But that same difference in identifications is officially on a bigger loop. So that means that on this space X, the curvature is smaller. Of course, this is a bigger space, so to speak. So that doesn't buy you anything. This isn't a way to make almost flat bundles. Oh, I'm going to make almost, well, it's a way of making almost flat bundles, but not over the same base. It doesn't give you anything interesting. We need to have a compact space once and for all, and we want to have bundles over it whose curvatures are going to 0. When we go ahead and do that, that reverses this construction. You then just go around loops. You choose some generators for the fundamental group. That gives you loops in your space. And those loops, as your bundles have less and less curvature, those are going to be closer and closer to satisfying the relations in the fundamental group. Okay, so the upshot is the following. Okay, for a sufficiently good almost representation, you get a bundle over that B gamma. I'm assuming that B gamma is finite. For sufficiently close almost representations, those bundles are topologically isomorphic. Okay, and that the rational Chern classes of any flat bundle, that means the ones associated to representation, those vanish, right, rationally, right? The theorem class vanishes, and that explains the Voiculescu example. And now, in order to do the higher dimension, to explain the Gromov-Lawson, okay, is I need a classical fact, which is that every even dimensional sphere has a non-trivial bundle on it. Okay, that bundle is sometimes called the Bott bundle. Okay, because Bott figured out what are the complex vector bundles over any sphere, and even odd dimensional spheres don't have any interesting bundles, but even dimensional spheres, there are sort of, if you ignore the dimension, they're all determined by their nth Chern class. The nth Chern class turns out not to be an arbitrary integer. It has to be a multiple of n-1 factorial. There's some, there's some beautiful consequences of that. But anyway, there's actually a smallest one. We know what it is. That's called the Bott element. It plays a very critical role in K theory. Okay, and oh gosh, I was supposed to introduce K theory and I haven't. Okay, so K theory of X is, it's a group that you build up out of the complex vector bundles, and you view two of them as being the same if when you add on trivial bundles of the same dimension, you get the same, they're isomorphic to each other, okay? And you also have to formally add in trivial bundles of negative dimensions just in order to make it into a group. Okay, so that's what the K theory of X is. Nothing that important to say. Just I'll tell you a theorem from the 1950s, which is that for any compact space X, you build this group out of X, and if you ignore subtleties like divisibility, like I just said, that even over the sphere, right, the K theory isn't exactly the cohomology, it's divisible. But if you ignore finite order phenomena, the K theory of X is just exactly the even cohomology of X. Okay, and that in other words, in order to understand bundles, all that you have to understand are the Chern classes. So, and if you're giving me things that I want to build a bundle, I know how to build them. Again, I might have to multiply. Okay, and this, a flat bundle over a finite complex always gives me an element of finite order in K theory. Okay, so if you gave me a representation, the thing it gives me in K theory is always finite order. It's not true for infinite complexes. If I went to an infinite dimensional n space, the element that's associated to a representation of the fundamental group is actually infinite order. Okay, so there are subtleties. And it's also not true for almost representations, right? That was the Voiculescu example, right? That if you have the almost representation associated to the Voiculescu guy, that's an element in the K theory of the two torus. The K theory of the two torus, by this formula, you know rationally there's a cube in dimension, corresponding to dimension 2, right? The second cohomology of the torus. And the first Chern class is detecting the Voiculescu example. So now I could get to the Gromov-Lawson example. Wow, I have 3 minutes before the end. It's as if this was a well-prepared talk rather than an awfully prepared talk, because I'm only halfway through the slides. Okay, so here M is going to be a hyperbolic manifold of even dimension. And I want to explain to you how to get an almost representation of the fundamental group. Okay? And the almost representation that I'm going to get, okay, what I'm going to do is I'm going to produce an almost flat bundle. Okay? And that almost flat bundle, you know, when you go around the loops, that defines the almost representation. Why will it not be a representation? Because the way it's built, it has a non-zero nth Chern class. Okay? Okay, none of the other Chern classes are non-zero because of the way it's after all, it's being pulled back from the sphere. The sphere has no cohomology before dimension 2n. Okay, so the thing that's detecting it is going to be this C sub n. Okay, so so now the curvature, when I pull back a bundle, the curvature of the pullback bundle is related to the Lipschitz constant of the map phi, right? So phi is a continuous function. Make it smooth. Do something. No trouble doing so. Because what is the idea, right? If suppose that I were to stretch, okay. Well, so then curvature would become bigger when I pull it back, right? Because a small loop here became a bigger loop in the target, right? A small loop here in the domain became a bigger loop in the range. So therefore, there was more accumulated differences to the identifications of the vectors. Okay, so, right, so the curvature gets multiplied by the Lipschitz constant of phi squared. Okay, remember it's a 2 form, so that's where the 2 comes from. So now we're going to go ahead and do it. Instead of taking something that stretches, you instead take something that shrinks. So instead of doing it on the manifold M, I'm going to take a big cover of M. That's what this MK is. So it has a projection map to M, which we'll worry about in a minute. But this M, I want to take a big ball, say use the fundamental group being residually finite. Okay, or maybe better take an expander cover if it's a suitable M. Okay, and now I'm just going to shrink down to this 2 sphere. So when I shrink down to the 2 sphere, of course, now the curvature gets much smaller, right? Because a small curve here gets pushed, right? It gets compared to an even smaller curve in the range 2n sphere. Okay, so now that this shrunk, you have small curvature. Okay, right? This closed curve here goes to that small curve there. So the curvature now has gotten smaller. So now what could I do? Okay, that's now a bundle on M. On MK. We talked about the fact that it's no big deal to get almost flat bundles if you're going to change the base. I want to have something on the original M, but here I'm going to now use the fact that this is a covering map. Since this is a covering map, for each point here I have K inverse image points. So just take the sum of all of those K vector spaces. Okay, that's what we would call the push forward. Okay, push forward requires some, regularity of the map, like submerge. It's like an integration over the fiber. Things are bad on singular fibers. You have to be somewhat careful, but there is a push forward when you have a bundle. You'd say a covering space. This is the picture of what the push forward is, right? If I have a covering space, and then over this point, I have these 2 guys, and at each point, I take the sum of those two vector spaces. Okay. So this is what, in representation theory, this is the induced representation. And if I have a finite index subgroup and I induce up to a group that contains it, I get a new representation of that group, and it'll also be finite dimensional. If it was infinite index, okay, then I'm leaving the world of finite dimensional representations. So you could do the same thing. And the point is that the curvature doesn't change with this pi star, this push forward operation. And that's because in some sense, operator norm is non-Archimedean. I know everyone's going to say, you're crazy, Shmuel. I mean, what's going on? If you're taking block sums, right? We're not summing the operator on these 2 vector spaces. We're block comparing them, okay? And the norm of a block sum of, right? That's what we mean by A plus B. That's the supremum of the norm of A and the norm of B. So using operator norms, right? Nothing changes. Okay? So that's the construction. You just go ahead and, right, you take this, you look at your manifold, you find a big cover that has a very large embedded ball inside of it, okay, right? That you could do just using residual finiteness, okay? And you push that ball onto the sphere such that the boundary of the ball, say, goes to the North Pole. The rest of the manifold you map to the North Pole. You pull back the bundle. The bigger the ball, the less the curvature, right? Because the bigger the ball, the faster you're shrinking. Okay? And that goes ahead and produce, so you pull it back, it's on a cover, so then you push it back down and you're on the original M. Okay? And my time is up, so I won't really tell you more about this. So let me just stop here. Okay. Marius, since I didn't finish, you have more work to do next week. I apologize.
Perhaps you could say one word, what Gromov and Lawson, how they formulate their theorem. Is it exactly about this approximation problem?
No. They formulate their theorem as follows. They said that any G mod K mod gamma, no G mod K mod gamma,
Okay, so we got this
hyperbolic. Yeah, no G mod K mod gamma
in some odd dimension.
Yeah, well, yeah, even if it's odd, I'll get to it in a minute. Okay, yeah, there are various tricks. Okay, one can talk endlessly about the answer to your question, Peter. But,
no, I'm just trying to understand what they were doing, because I think I heard Gromov lecture on this, and now I can't remember what he was saying. So
yeah, no, but the theorem was that G mod K mod gamma does not have a metric of positive scalar curvature.
Ah.
Okay, that was the theorem. This was a lemma. Okay, and the connection is the stuff that is related to the things that I didn't explain, which is that firstly, there's an elliptic operator around and there's an index around. The index is what begins connecting things to K-theory, the Fredholm index that occurred in an early slide. Okay, and one thing is that an argument that goes back to Atiyah, Singer, and Lichnirowitz showed that if you had positive scalar curvature, then some index is 0. They said if you twist by suppose your curvature is bigger than 0.5, and you twist by a bundle whose curvature is less than 0.25, then even that twisted thing still has positive scalar curvature. So they said, if I had almost flat bundles, I could twist operators by them, and I still will get non-zero indices. But then they said the bad news is if I twist by a flat bundle, I get nothing. So they looked for almost flat bundles to twist by in order to get more information. And they saw that for even dimensional cases, they knew what to do. And then for odd dimensional ones, they crossed with a circle and said they were even dimensional.
Mm-hmm. Thanks.
Okay.
Yep. That's maybe, Alex, we need a second lecture by him, I think.
Yeah, we probably.
Because I think there's a lot of very beautiful information here that he was going over a little too fast. I have one comment, Shmuel. Yeah. Your handwriting in the beginning was not your handwriting. That's clear.
That's true. That was a font.
Okay.
At the beginning, I was like, wow, what happened?
I have to admit that it was also a bit fast for me, even though I talked in the last few months, I talked a lot with Shmuel and he already explained some of it. I just want to remind myself and everyone else that the lectures is recorded and in few hours it will be on the Institute website. And we will check the possibility of having more lectures. The problem is that in the slot of this seminar, we are already have a lot of plans. So we'll think what to do. May I ask you just a short question, Shmuel?
Of course, yeah.
We know that the conclusion is not true for the P norm for P less than infinity, some of these conclusions. Right. Now, are you using the fact that this is operator norm only at that last point when you show that this sum up, when you do this induction, that the norm, or there is any other point where this is used?
I mean, I would have to, I haven't thought about the business about associating bundles and Chern classes and continuity for other norms. Right? I mean, there are other things to check, which I haven't done. So the answer to your question is, at the moment, I don't know. I have to think about it. So. I mean, I'm not saying it's hard. I'm just saying I don't know.
I just want to remind the people here that we know examples of complexes of even dimensions, which are stable in the P norm. In fact, for every P large, not infinity. So it's really an interesting distinction between the case of P equal infinity and P less than infinity.
Shmuel, I'm really glad you spent 20 minutes on the example at the beginning, even though it took you, landed it up that you wouldn't be able to finish, because it was a beautiful example. Well done.
Well, you know, like I said, nothing here is due to me and nothing here is new. You know, I mean, it's just, you know, I mean, I think it's a beautiful story of mathematics, you know, and, you know, just a little hard to compress, you know, many decades into 1 hour. Okay.
Yeah, it's really a pleasure. We started with testability in computer science and we arrived to K-theory. That's wonderful. At some point, we will come back to computer science. And anyway, we are all looking forward to next week's talk by Marius, who will give us a little bit more of that kind.
Right. And Marius, I don't know how much of this is really a prerequisite for your class, for your talk. I mean, it might be that, you know, but I tried.
Very helpful indeed.
Okay, good. All right. Okay, goodbye, everyone.
Thank you very much. Thank you.